is it viewable?
Yes.
Okay, very good. Yeah, so we talked a little bit about regularization last time, not very much, but a little bit. So we were going to go more into depth in this lecture here. So it's as we had just been talking about, it will help you when you have variables or columns that are very highly correlated, and when you get matrices that are singular. But it's in machine learning, it's mostly a tool to avoid overfitting by putting some restrictions on the parameters that you find when you do optimization in machine learning. And it's also necessary just to get convergence in our descent sequences. So we've seen gradient descent, and that does not always converge. And here's a very simple example of that. So we're going to we have a data set here with two data points. It's a two-dimensional data points, -1, and 1, and labels -1 and label +1. So I could make a quiz here, think, what do you think is the line that separates these data sets into the label -1 and label +1s? And you probably would be able to answer that, so I'm not going to post it as a quiz. But how would we do that? Suppose we couldn't figure out how to do that sort of by just eyeballing it. We want to do a logistic regression. So we would have to write up our logistic regression loss function, and that is what we defined last time here. So the logistic regression loss function, when we have a labeled data set, so this is a general framework here. We have a labeled data set. We have data points, data vectors xi, and we have their labels yi, and yi in the logistic regression case is plus or minus 1. And then we had defined this loss function. There's a missing one over n here.
One over n.
We had the loss function here is given by this somewhat strange expression here. We had this logistic function that you remember as 1 over 1 plus x per minus z. And we evaluate this logistic function on the dot product beta dot xi. So xi is our data set. The betas are the ones we're trying to find. These are the coefficients we're trying to find. And the yi are the labels here. And so the loss function was given by this expression here, the average over the log of the logistic function applied to yi times this dot product. Here's a logistic function. Here's the dot product. And this is the one we're trying to find, the beta here. And so the way we did it was we wanted to minimize this loss function. We want to find the beta that minimizes this loss function. That's where we used logistic descent to gradient descent to do that. So let's see what we get now in our case here. In our case, we have just 2 points. We have this point, and here the labels -1 and +1. And so the loss function here is 3 variables, beta 0, beta 1, and beta 2. And here's the loss function. I've written it out here in great detail. So it's minus, and then we have the label here for the first one. That's -1 times, and then we have beta 0 times, that's always there. And then we have beta 1 times the first coordinate plus beta 2 times the second coordinate. So that's what we have. That's simply what we have from this. That's the term we get from this data point. The other data point is labeled +1 and beta 0, and then we have 1, 1. So it's beta 1 times 1 plus beta 2 times 1. So this is the logistic regression loss function we have here in this simple case. And so what are we trying to do? We're trying to minimize this. We're trying to find beta 0, beta 1, and beta 2 that minimizes this. And that means we're trying to find out where's the gradient 0, where's the partial derivative 0. So we can rewrite this a little bit, and I'm not gonna do all the computations here, but using this well-known fact, the log of 1 over a is minus log of a, we can rewrite it like this, and then take derivatives, partial derivatives back to beta 0, beta 1, and beta 2. And I've written them down here, so there you can look at the notes I posted. So that's simply applying usual rules for differentiation. You get these things here. So we want to put those equal to 0 and see if we can find beta 0, beta 1, and beta 2. So we can try to do that. And I'm just going to give, instead of writing these all the time, I'm just going to give this term here the name A, and the other term here the name B. You can see this is sort of the only terms that appear are these terms here. And they appear then with different signs on them. So I only have these two A and B. This is A and this is B. These are the only two things I really have to compute. But if I try to write down the equations in terms of A and B, then I get these two equations here. I get three equations, but two of them are these. A plus B is equal to 0, and A minus B is equal to 0. Now the only solutions for these equations, that's both A and B equal to 0. And that would mean that, for instance, we would have A here equal to 0. But that can't happen because the exponential function is never 0. So this A here given as this fraction here is never 0. And so that means that these equations here, they don't have any solution. These equations, putting them equal to 0, they don't have any solution. So there is no minimum here. And so that's bad, because that's what we need to in order to use logistic regression. We need to find a minimum here, but there is no minimum. So this loss function does not have a minimum. And what do we do then? Well, that's where regularization comes in. So that's another very good reason for using regularization, as we saw here. If you don't use it, there is no solution. But let's try to regularize. So let's put in.
Can I make a point?
Go ahead.
Vis-a-vis the conversation we had before, that case corresponds to determinant 0. You know, so you can't solve the equation with determinant 0.
Yes
1,
and no. I don't, that I'm,
well, A plus B, A minus B. It's really.
Yeah, that doesn't have a solution, but that's right. That's,
but morally, this corresponds to the fact that there is a determinant that can't be inverted.
Right. Yeah.
Anyway, that's what I've always said about it.
Well, right. But it definitely doesn't have a solution.
That we agree.
So let's try to regularize it. And so that means we add a term like this. So we sort of, for many reasons, don't regularize on the constant term here. So this is sort of the one that corresponds to the 1 in the. So that's a constant term in the equation for the line that we're getting. So for certain reasons we don't regularize over this. So we don't only we only try to limit the size of beta 1 and beta 2. You can regularize over all three if you want, but there are reasons why we don't do that. So our loss function, our regularized loss function is now this. So we've added this this term here, and let's see what happens if we try to minimize this one instead. So we couldn't minimize this one alone. Now we added this term here, and let's see if we can minimize that. So
I have a question.
Yeah.
In the regularization term, why beta naught is not there? Why it's a function of only beta 1 and beta 2?
You can do it, but it's common not to regularize over the beta 0. The beta 0 just don't really have anything to do with the data in the sense it just gets multiplied by a 1 all the time.
Okay.
These things here, they get multiplied by the coordinates of the data points.
Okay.
So it's you can do it. I mean, it doesn't make things go wrong if you do it.
Okay.
But let's just try to see what we get now for the partial derivatives here. So the last term, well, if you take partials here, it's the partials of this plus the partials of this. So it's very easy to take the partials of the sum of two functions. The first one here, that's doesn't involve beta 0 in the second term. It's only involved in the first term. So that gives the same derivative with respect to beta 0. So we take the partial of the regularized function here with respect to beta 0. It doesn't change anything because this is just the partial derivatives of this function here with respect to beta 0 is just 0. So we get the same, a plus b. Mm-hmm. Then we take the partial with respect to beta 1. So that gives us the partial of this one with respect to beta 1 plus the partial of this with respect to beta 1. Well, the partial of this with respect to beta 1, a minus b with respect to this one with respect to beta 1 is just 2 lambda beta 1. Down here, with respect to beta 2, it's a plus b, and then the partial with respect to beta 2 here, which is 2 lambda beta 2. So we get these three equations here. So these are the partial derivatives of the regularized loss function.
Hey, Niels, just want to, it's a minor thing. There is a typo there on the last line. It should be 2 lambda beta 2. Partial with respect to beta 2 is the original term a plus b plus
here it should be, yeah, you're right.
Yeah.
Here, yeah.
Yes.
Right. So so let's see, can we solve these equations here? And well,
Professor, can you go slide by? I just want
what's that?
to understand how the partial derivative with respect to b1 is a minus b. I just want to see the previous slide. I guess I didn't follow that.
Yeah, because that's just to not have to write this all the time here.
Right.
Right. So this is I introduced this notation A and B for these. So if you go back here and see what you have here, it's A plus B here and A minus B here and A plus B here. So you can see what these expressions here for the partials in terms of A and B just gets yeah, you can see these two are the same, right?
Right.
So A plus B, and this one is the same with a minus here. So yeah. So yeah, so the three equations that we had before we regularized, A plus B, A minus B, and A plus B are all equal to 0. Now we have this extra term here, and they're still equal to 0. So that gives us A plus B is equal to 0. So this must also be, so this is 0. A plus B is 0. So that gives us that beta 2 is 0. So beta 2 is 0, and that means it drops out. And what we end up with is this equation here. And you can see that if we, so these are almost the same here. There's a minus here. So if we put beta 0 equal to 0, then this term here and this term here are the same. And this one has a minus in front of it. So in that case, it's 0. So if we have beta 1 equal to 0, or beta 0 equal to 0 and beta 2 equal to 0, then the partial derivatives are in fact equal to 0. And so that means that a minimum is of this form, 0, comma beta 1, comma 0. And any point of this form will have all three partial derivatives equal to 0. So this is the minimum. This is the minimum of the regularized loss function. And so what is the line that the separating line that this one this point here, this beta here defines? Well, that's beta 0 plus beta 1x plus beta 2y equal to 0. And so this is 0 and this is 0. So it's beta 1x equal to 0, which we can also say that's just x equal to 0. So the separating line is the line x equal to 0. That's the same as the y-axis. Right.
That's what I guessed, by the way.
Good. Yeah, you're a good student, Adam. So
Yes.
you got it good. So even so, going through all this stuff here, we can see that the regularization gives us the right answer. But if we didn't regularize, we could not solve this problem, though we could.
Adam and I guessed it before doing all the math.
What's that?
Adam and I guessed it before doing all the math that it will be x equal to 0.
Right. You get a star.
One of the questions that I had was that
Yeah.
the choice of the word regularization.
Yeah.
If you could just two sentences on that, as well as was there anything specific to the example that we chose that caused the first order loss function to not give us, and the second order loss function to actually give us a minima? I mean, I shouldn't call it a second order loss function, but the second form of the loss function.
Yeah, there is. It is in fact true that if you have at least a two-dimensional, if you have a two-dimensional data set, so your data vectors are two-dimensional, and they can be separated by a line. So if you have a whole bunch of things like this, so let's say you have data points here, and here, and some. If they can be separated by a line, so that normally you can't separate it completely. So you try to find the best line, and then that's the one that misclassifies the least number of points. But if there are no points that are misclassified, so you can find a line that completely separates the two, then then you will not have a solution. There won't be a minimum of the unregularized loss function. So this is
very counterintuitive. I mean, from a non-mathematical point of view, this is extremely counterintuitive. That here you have a data set that exhibits perfect information, and we are unable to capture information. For data sets that do not exhibit perfect behavior, we're able to capture that.
Exactly.
So maybe an intuition is to say, if they're perfectly separated, it's kind of like the boundary is one-dimensional. It's like a linear one-dimensional thing. And then you're getting into the determinant equal to 0. And so something along those lines. The same way, you know, if you have two lines, they normally will meet in a point, but if they're parallel, they don't. So
fair point.
Simple case of two parallel lines, you know, funny things happen.
It's not so hard to prove it actually that it does. You can. If you try to sit down and try to prove it, you probably can. It's not so difficult because you just say, okay, I have two data sets and I have a line that completely separates them, and then show that there is no the partial derivatives do not have a common zero.
But Niels, kind of speaking like a physicist, the situation is that if you wiggle the line a little bit,
yeah,
there is no change to the loss, significant change to the loss function because the points are perfectly classified. There is no penalty, right? So there is a degeneracy. There are many equivalent lines that differ by small deviations that do not change the loss function significantly. And the moment you add that quadratic term, that degeneracy is broken.
Yes, that's
No, but even if you wiggle the line, Vijay, it won't be you're saying that the line will be quadratic, which will be separating.
No. Right now, if you just wiggle the line a little bit about the
yeah, but I mean that's you sort of have well, I mean you can have a situation where you have a point here and a point here. And
yeah.
So you can wiggle it. Yeah.
Points all on either side of the x-axis, then this degeneracy will get kind of broken, right? But we are talking about a continuum limit here, so you're never going to get that many data points to fix this line. So
no, you're not going to get infinitely many, but it's still yeah, right. But
so in other words, the minimization we're doing is trying to rotate this line and see whether the loss function increases as we rotate this line, right? If there is no way to rotate the line without increasing the loss function, we found the minimum.
Yes, that's true. But yeah, I mean that's certainly true a bit. But the thing is that I mean in general, when you don't have total separation, right? Then you will have I mean then you can sort of wiggle your
but now additional points will get classified, misclassified, or classified. So your loss function will change a little bit.
Yeah. Then your loss function will change, right? That's right. Here it's I mean here it's it will not change because it's I mean it's separating. So every point is, but it's as I said, it's not so difficult to prove it that. Because every point is perfectly classified, right? And it's,
but I think Niels, what I was trying to highlight is maybe it's not it's not because every point is perfectly classified or not, but there are many equivalent lines that have the same penalty, right? And therefore the minimization is not able to pick one of them. Right? So if you're trying to find, there's no.
But Vijay, sorry, if I can say that your argument would be true in any case, right? In any defined, non-defined, well-classified, non-well-classified situations, your argument may well be true. Then why stop only at the square term? Why not say that, well, you can now nail it down further by adding a fourth power, fifth power, sixth power?
No. The idea is, first of all, in general case where the points are intermixed, if you wiggle the line, you will typically change the loss function because one point will be adversely affected or another, right? So the general case is in some sense slightly better behaved. Why the quadratic function and not some other function? Quadratic is nice in many ways. The U-shaped function.
You could use another function too.
Yeah.
In this case, you could obviously use any power function. That would give you the same answer. That's.
Just a small question here. What if you used this in places where you did not need to use it? How would that change? Does it ever get it to misbehave, or it is only a decaying factor, so you'd never get it to misbehave?
Sorry, I didn't understand your question. Say it again.
No, let's say we did not achieve a situation where we ever had to we could not minimize the loss function in the first power. And then we went ahead and said, okay, because I have to write a computer program, so might as well add the loss function at second power, third power, fourth power, fifth power.
That's right.
Would I be making some kind of broader generalization than I should have, or you should only use it when you need it?
No, you wouldn't. I mean, it's that's why in scikit-learn, they automatically regularize. I mean, you can change the degree of regularization by changing this parameter lambda, right? So we put in this parameter lambda, which sort of determines the amount of regularization that we put in. So the larger lambda is, the more regularization you put in. So lambda has, as soon as lambda is non-zero, you have a regularized problem. And in sklearn, you always have a non-zero lambda here.
You can also point out, you can change, instead of beta 1 squared plus beta 2 squared, you can use different powers.
Yeah. That's
how.
Right.
But, you know, maybe the point of this is the function doesn't have a minimum. What that means is, you know, no matter how large you go, you can get smaller and smaller values, right? So what this regularization term says, all right, I understand the minimum is basically out at infinity.
Yeah, that's it.
Okay, because there is no minimum. You know, but if you sort of go out to infinity, it can't be blowing up. It can't be getting too large and larger, because if it keeps getting larger and larger as your betas get larger, that would mean inside that smaller space there was a minimum. If it's always bigger when you go further away, then this the smallest value somewhere in the middle. So it has to keep getting smaller and smaller and smaller. So you can make it really close to zero by taking beta 1 and beta 2 and beta 0 really large. So when you add this regularization term, it says, okay, I know you can't do it, because as I make my bigger and bigger balls, my values get smaller and smaller. But what's the smallest I can get inside this ball? Now, you know, it's arguably on the boundary, but there is a minimum value.
Right. Yeah, I mean, that's
minimum
exactly right.
On sets that are bounded.
That's exactly right.
Compact is the correct technical word.
Right.
But
yeah, the truth of the matter is that the unregularized loss function, it does have a minimum, but it's just at infinity. And but we can't really deal with infinite number here. So when you regularize, you only look at things inside a bounded set, and that's why then that minimum will be at the boundary. That's what happens. But any convex function does have a minimum, but that minimum may be at infinity. If you try to draw this, you'll see that if you draw a one-dimensional slicer, you see that it decreases, the derivative decreases very, very slowly towards zero at infinity, but it never gets there. So once you sort of enclose it in a ball, then it'll at the boundary it'll be the minimum. So that's that shows that that's certainly one reason why regularization is very important, and it is you will always in practice always include a regularization term with a non-zero regularization parameter. You can make that regularization parameter very, very small if you don't want to regularize too much. So that is one reason why we regularize. So another thing that we saw last time was the convergence rate of gradient descent can be painstakingly small. It can be so small that in practice you can't find the limit using that. And we saw that even in sklearn, you didn't find the right minimum using that. And now there are ways you can change that in sklearn to actually find the correct minimum, but I will just now I'm not going to go through all the math here because it's a little complicated. But you'll have to look at the notes here. But the idea of Newton's method is to, instead of just using first order data, namely just using the first order derivatives of the function, we get the gradient descent. But if you use second order, you get another method called Newton's method, which converges very, very fast. And let me just not go through all the details, but the idea behind the gradient descent here is that you can approximate a differentiable function with a linear function. And so the linear approximation to a function is f plus delta x is almost, or is close to the value at x plus the derivative of the function at x times the delta x. So that's the linear approximation, and then by using some theorem from linear algebra, you can show that in fact the fastest descent you get here. So when you want this difference here to be as small as possible, and that happens precisely when this delta x here is a multiple of the gradient. So it's in the same direction as the gradient, and you want this to be negative, so you want this to be 0. But you can also use a quadratic approximation to f. So this is a more complicated expression here, where you have the f of x plus delta x can be written approximately as f of x plus the gradient of f times delta x. So this part here is the same as before, but then there's an extra term here that involves the double derivatives of f, and that will have delta x as a quadratic term here. So this matrix here, not the square here, as I call it here, that is the matrix of double derivatives. So you can, when you have a function of several variables, you have its gradient, that's the partial derivative x of partial derivatives, but you also have if it's also twice differentiable, you also have the double derivatives. You can take the derivatives with respect to one variable, and then you can take the derivative of that with respect to another variable. So you have all these cross derivatives here. So that's what I've written up here. This matrix here is the what's called the Hessian. So that is a matrix of all the mixed and also the double derivatives with respect to the same variables here. That's down the diagonal. So that's a matrix of dimension d, where d is the dimension of the variable x. So if we use that, then we get, again, I'm not going to go through the math here, but if we use that, we get a particular delta x that we should use in our gradient descent sequence. That says take this Hessian, take the inverse matrix of the Hessian and multiply that onto the gradient and take the negative of that. That is your delta x, and that's what we use in the Newton sequence. So again, we start with some x, then we compute this delta x here, and then the next one we use is x plus delta x, and then we do the same with this new, so this is now x1, and then we do the same next time we get x1, and x1 plus delta x1, that's x2, and we continue this way. And that is going to converge to a minimum, and it converges very, very fast. So I've done it for logistic regression here, computed all the double derivatives and stuff. I'm not going to go through this because I would get confused myself if I did that. But you can easily follow by if you go read the slides, you can easily follow along and verify the computation. So
then on the previous slide, sorry, one question. So on the previous slide, with the expansion of fx plus delta x you were doing, in one dimension, is this what a Taylor series is?
Yes, that's a quadratic Taylor.
Okay.
Yeah, a quadratic Taylor polynomial, exactly. I mean, it's a polynomial. It's a quadratic polynomial in
okay.
delta x. What happened? So I computed this, as I said, I computed the Hessian for the logistic regression loss function, and you get a sort of a fairly nice formula. It's not so difficult to program. And in fact, also the code file I gave you also has the code for how to compute the Hessian. So I have applied this to the data set we had last time for the temperature and the loss function of the Challenger data with the temperature. And so as you remember that we started there at the starting point of 0, 0. So beta, we started with 0, 0, and then we used gradient descent, and we never got to the true minimum of the function. So let's try to, instead of using gradient descent, let's now try to use the Newton method here. So this is what we're doing here. So here we start with a B, and then we take the inverse of the Hessian. So I've computed the Hessian up here in code here, so you can also try to run this code. And then I multiply that by the gradient, minus the gradient, and then I have to take a minus, it gives me plus here. And then I can run this, so I run it only for 10 iterations here. And you can see here, the result I get here is that this converges already within 6 or 7 steps. So after we get down to here, there's no change in the level. So it's converged already in 5 or 6 steps. So this is and you can see here we get the correct minimum now. There was about this 15 comma minus 0.23 or something. So that was the same we got from the other methods. So this Newton method here is very, very fast. It converges very, very fast if it converges. I mean, if there's no minimum, obviously it does not converge. But it's a little harder to compute, right? Because you need this second order information, these double derivatives. So it takes a little longer to compute. But you can also use this method in sklearn. So what you have to do is here is the logistic regression class, and here we instantiate a logistic regression classifier. Instead of, if you don't write anything here, then it'll use the solver liblinear, which is the gradient descent. But if you use other solvers here, this is LBFGS, so this is a low memory. I can't remember this. Braden, Bano, Goldfarb, and Shannon or something. There are 4 guys who invented this optimizing method here. If you use that instead, then in fact you do get the right result from that. So if you're having a problem with getting your logistic regression from sklearn to converge, you can try to use another solver. There's also a Newton. I think in the code I posted that it's a Newton CFG or something. That's another solver that uses the Newton method. So you can do it with sklearn also. So here
sklearn will by default use the liblinear, the linear term which converges very slowly.
Will use gradient descent. So it will not converge.
So sklearn by default uses liblinear solver.
Right. Exactly.
Right.
That's
Okay.
Right. That's the fastest. That's that's the fastest.
Okay.
So this one it takes a little bit more computation because you need to compute the second order.
Okay.
So here's sort of what it looks like when we do this in a one-dimensional. So we start with this point here, and here the green one is the quadratic approximation, and the orange one here is the linear approximation. And so what the Newton's method does, it said, okay, I'm going to approximate my curve with a quadratic one. And then I'm going to say, well, the minimum of this quadratic one is probably going to be close to the minimum of the curve I'm approximating. So here's the minimum of the green curve. That corresponds to this point here on the blue curve, which is the actual one. So that means that the next point we're getting is this point here. And then we do the same. We find the quadratic approximation that approximates the curve at this point here. So that's, again, this green curve here. And then, again, we say, okay, this quadratic one is close to the curve. That means that the minimum of this quadratic one is probably close to the minimum here. So that means the next point we're getting is here. And you can see here from this, keep doing this a couple of times. You can see the green curve here, the quadratic curve, is now very close to the blue curve here, and the red point here is very close to the minimum. Here, in fact, we are at the minimum. The green points here, those are the ones we get by using gradient descent. You can see it goes much faster here, much slower here, rather. It converges much slower. It's much further from the minimum than the red one. Also, you can play around with the code that I posted, and you can sort of see how this thing works. I put a little piece of code in there, so you can run this algorithm a number of times and see how the Newton method converges much faster than the gradient descent. So we can also use Newton on the regularized function, of course, and that is again pretty simple, because again, all we have to do is to again, taking the double derivatives, again, it's just the sum of the double derivatives of the loss function, the unregularized loss function, and the double derivatives of the regularization term. And the regularization term is, if you use quadratic regularization, is very simple, right? Because what's the partial derivative of this beta 1 squared with respect to beta 1? Well, that's just 1. If you take double derivative, first derivative is 2. So it's 2 beta 1, and then the next time you take the derivative of that with respect to beta 1, you just get 2. So it should be 2. That's why people prefer to put a 1/2 here. So the Hessian of the regularization term is just this matrix here. We left out the beta 0, so we get a 0. So it's just a matrix that has ones down the diagonal, except for the 0 up here, and then you multiply it by. So this is a very simple term. You're just adding that to the you're adding this to the Hessian of the
loss function,
unregularized loss function. So it's very simple to regularize the Hessian. And also there's some code here that shows how you do this. So this is computing it for the regularized thing. So one thing you should notice here is that once we do this, once you regularize, and now I'm regularized with a somewhat larger regularization constant 6 here, then you can see what happens is that the actual solutions you get, the betas here, are much smaller than this. So before, the minimum was at 15 or something, and now it's much smaller. Now it's the constant term there is 6.98, and the other term is minus 0.11. So you're getting different minima. So that's what happens when you regularize. your minima is going to be different because you're restricting your minimum search to a smaller subset. So you're going to get smaller. You're going to get a ball, yeah. And so they'll be smaller. And so that's not something to be afraid of because that's to be expected. That if you regularize, you're going to get a different minimum than you get on the unregularized. So logistic regression in sklearn always uses regularization, but they do it by putting lambda equal to something of the form 1/c, and so that can never be 0. And so, but that means that the bigger c is here, the smaller lambda is. So you have to be careful when you're doing sklearn. When you regularize, a very, very large constants there corresponds to a very, very small regularization parameter. So that's something that Adam in particular is really pissed off about. But that's to make sure that you always regularize. So you should always get a solution in sklearn. Yes, I will not. So here's the regularized logistic regression using the LBFGS thing. So I will quit here because Adam has a lot of stuff to talk about. So I will. So there's some. So you should submit your homework, right? And we have made another homework here, which is somewhat simpler. So we're only going to give you 1 week to do that. And so they're at the end of these. Okay, so next is Adam, and let's see.
So I have a couple of questions. So logistic regression, which we did so far, it used 2 labels. But it may very well possible that we are dealing with a data where you can have 4 or 5 labels, like 1, 2, 3, 4.
Yeah, that's right. Yeah, that's right.
We still can't do linear regression. We have to use logistic regression. So it's still possible, right?
It's still possible to separate those. Yeah, definitely, it is. There's another technique, which is a generalization of logistic regression, which is called softmax regression, which allows you to do when you have multi-label, multi-category categorization problems. So you can do that. You can also sort of do it one at a time, right? You separate